So this is set 4. We're going to find the basis, dimension, and solution space. The first thing you need to do is to take this 1, 1, 2, 1, 2, 1, 1, 0, 1, 3, 2, 3, 0, 1. I appreciate their spaces there. That's nice. 2, 3, 2, 2, 5. And you're going to take that and put it into reduced row echelon form. That's what you're going to do. Okay, so in doing so, I need to hear what you get. 2, 3, 4, 0. Yep.
0, 1, 0, 0, 0. 0.
Okay.
0, 0, 1. 0. Negative 1 half.
Negative 1 half, I agree with. 0. And then 0, 0, 0, 1, 3, and 0. Okay. Did everybody, well, it's easy to do a keystroke mistake on these. And I'm going to set this background like that. All right, so once you have it that way, label this x1, x2, x3, x4, x5. Okay? And we're going to let x5 be equal to t. What will x4 be? X4 is going to, you're going to move this over and it'll be negative 3t. Do you want me to show you that step or are you okay? What will x3 be? One half t. What will x2 be? Excuse me. 0, x1, 0. Okay? So now we're ready to set up the solution space. The solution space for x1, x2, x3, x4, x5 is going to be pretty easy if you multiply it by t. What's x1 again? How many t? 0. x2? x3? 4. And x5? Yeah. This is the solution space. Isn't that cool? Come on, that's cool. You just did it. But what's really neat about this is that you have a basis now of this. This is my basis. 0, 0, negative 1 half, negative 3, 1. And what's the dimension of the basis? How many of those are there? Yep. That's dimension of S. Is 1. Ta-da! That's it. Come on, that's not bad. It's not bad. That's not bad. You try one yourself. Put your money where your mouth is. I'm not going to go over this one. If you see these, just jump for joy. These are so doable. You have C1 times 1, negative 1, 1, plus C2 times negative 1, 1, negative 1, plus C3 times 2, 0, 1. That should, linear combination, if you find these, you should get negative 3, 1, negative 2. This is kind of a simpler version of what we're doing with the eigenvalues, isn't it? Kind of. There's a connection there. You're finding the constant. When you multiply this and these other constant multiplying by these, you're going to get this. So if you multiplied those through, you get C1, negative C1, C1, plus negative C2, C1, negative C2, plus 2C3, 0, C3, equal to negative 3, 1, negative 2. So when you put this into one big thing here, you're going to get C1, C2, C3 multiplied by 1, negative 1, 2, negative 1, 1, 0, 1, negative 1, 1. I'm not going to do these in between steps, but could you see me putting these all together and then factoring out the C1, C2, C3? I mean, why do that extra right? So how are you going to solve for this then? How are you going to solve for this? Yeah, you're going to do the inverse. You're going to do the inverse of this, and you're going to do the inverse here. And so you're just going to take 1, negative 1, 2, negative 1, 1, 0, 1, negative 1, 1 inverse times negative 3, 1, negative 2. That'll be equal to C1, C2, C3. This is what we did a couple chapters ago. Now, that's how you get the matrix product. Well, yeah, go ahead and do that. Tell me what C1, C2, C3 is. I'm going to show you two ways to do this. This is a really good way to do it. Anybody get some decent answers for those? Does that look right? 0, 1, negative 1. Okay. So now we got to go back and look at what the problem asks. Write this as a matrix product. So what you're doing there is you're saying, okay, as a matrix product, C1 is 0, C2 is 1, C3 is negative 1. Okay? So the matrix product is going to be double check here, make sure I'm doing it right. Yeah. 0 times 1, negative 1, 1, plus 1 times negative 1, 1, negative 1, plus actually minus 1 times 2, 0, 1. And notice that 0, negative 1 minus 2 is negative 3. 0, 1 plus 0 is 1. 0, negative 1 minus 1 is negative 2. There is your matrix product for your linear combination. Now,
it didn't work for me to find the inverse.
Yeah.
you couldn't find the inverse?
Yeah, I think it's 2 times 0.
Really? That's weird. Do this for me. Take 1, negative 1, 2, negative 1, 1, 0, and do reduced row echelon. Do reduced row echelon for that. That should work. Okay, and so if you did that, I got reduced row echelon form. Okay, if you do that, you should get for 3, 1, negative 1, 0, 1, negative 1, and you should get 0, 1, 0, 0, 1, and negative 1. Is that right? And 0, 0, 0, 0? Is that correct?
Yeah.
Looking at 3 here, and I got 1, negative 1, 0. Yeah. And so with this, you should get C3 is equal to negative 1. C1 minus C2 is equal to negative 1. So C1 minus C2, C1 is equal to negative 1 plus C2.
You know where the negative ones look like on the phone? Did anyone get those?
I got it from including in the fourth column. Negative 3, 1, and negative 2.
Did you?
You have to include the, you can't just do a 3 by 3, you have to do a 3 by 4.
Yeah.
But is the fourth
Why?
column all zero?
The fourth column is negative 3, 1, negative 2.
Oh, that's what I did wrong. Yes. Thank you. Negative 3, 1, negative 2. There you go. Now we can do it, I bet. Now it'll work? I don't understand why this turned out this way. C3 is negative 1. Okay, that's 3. Let's go on to number 4. 4 works out a lot better. Determine whether it exists in a subspace. So for the subspace, you have to prove closure for addition and scalar multiplication. That's what you have to do. So we're going to let u, vector u, be equal to, and then we just use these, u1 minus 3, and u3. And then they said, because z is different than x. Then v is equal to v1 minus 3, v3. And we have to show that if you take u plus v, you're going to get essentially this plus that. But watch what happens when I do that. u1 plus v1, u1 minus 3 plus v1 minus 3, u3 plus v3. Is there a problem here? What is it, Ben? u1 plus v1, u3 plus v3. That looks good. But what's at the top? u1 plus v1 minus what? 6. And since this is not equal to 3, or negative 3, we would say that u plus v is not an element of the sum. And so we would say W is not closed under addition, therefore not a subspace of R2. Yeah. What are we looking for here when we say we want to see if this linear combination here of basis is going to span R cubed? What does it have to do? It has to have spanning requires what? Linear combination. Linear combination. So what you can do is you're saying that there exists a C1 101 plus C2 1 negative 1 0, etc. That's what you're saying. Okay, now we can prove it instantly by taking that matrix 1 0 1 1 negative 1 0 negative 2 3 1 and taking the determinant. And if that determinant is equal to 0, that tells you what? No inverse, and it doesn't span. So go ahead and do that. go ahead and take that determinant. Okay. You can use your calculator, or I would just cover up what's underneath the 1, the first 1 here. And that'll give you negative 1 minus 0, which is 1 times negative 1 minus 0. Minus, now we're going to do this 1. 1 times 0 minus 3. Plus negative 2 times, cover this up, 0 minus negative 1 will be 0 plus 1. So this is going to be 1 times negative 1 plus 3 minus 2. What's that equal to? 0. Therefore, A inverse doesn't exist. Therefore, W does not span, what is it, R3. That's a quick way to check it. And last, oh, this was the last one on this set. I'm going to save that.